Good evening, ladies and gentlemen. I think we'll make a start. Welcome to this first lecture to be given by this year's Humanitas Visiting Professor in Sustainability Studies as part of the Cambridge University Festival of Ideas. My name's Mike Rands. I work with the Cambridge Conservation Initiative, one of the growing number of bodies here in Cambridge working to achieve sustainability in the use of the planet's living natural resources. And it's a real pleasure to be here for this particular event. The Humanitas Professorship is hosted here in Cambridge by CRASSH. That's the Centre for Research in Arts, Social Sciences and Humanities at the University, in association with the Institute for Strategic Dialogue, the University's Conservation Research Institute, the Cambridge Conservation Initiative, and is generously supported by the Talus Marta Foundation. Cambridge, I could have given you all the acronyms for those and you wouldn't have understood a word of it. Cambridge is full of such things. We have with us today a very distinguished person, a pioneering scientist in sustainability as the visiting Humanitas Professor, Professor Johan Rockström. He collaborates all over the world with others to develop big ideas and strategies around focusing on resilience and sustainability. He's currently the executive director of the Stockholm Resilience Centre in Sweden and teaches natural resource management at Stockholm University. He was previously the director of the Stockholm Environment Institute, and like all people who carry those sort of titles, he sits on numerous committees and boards and other institutions all around the world relating to environment, development and sustainability. In 2009, he was awarded the title Swede of the Year. I have yet to find out what that meant, but I think it was for his work bringing science and policy together around climate change. And later, the following year, he was ranked as the second most influential person in Sweden in relation to the environment, which I have to say leaves us all wondering who the first one was. However, at this time in history, when we as people are having so much impact on the planet, and we know our population is growing, we know the resources are finite, we know if you're a glass half empty person, this is the biggest environmental crisis the planet has faced. If you're a glass half full person, you believe we've never been better off and technology will solve all the problems. Wherever you sit in that spectrum, there is no doubt that we need people with new, big, exciting ideas, ways of communicating and thinking about the issues of sustainability of the environment. And we couldn't have a better person today to talk to us about that than Johan Rockström. He's developed the whole concept of planetary boundaries. I won't steal his thunder by trying to explain it because I would do it very badly, but that is what he has been doing over the last few years with leading academics and practitioners and policymakers around the world as a very important and exciting contribution to this whole arena. So I'm delighted to welcome him and introduce him and invite him up here to give the first lecture in this series entitled Human Prosperity Within Planetary Boundaries. Yeah.
Thank you so much, Mike, for those kind introductory words. And let me start by saying what an enormous honor it is for me to be this year's Humanitas Visiting Professor in Sustainability Studies. I'm grateful that you went through the fantastic group of institutions backing this, because I would have stumbled along the way, but it's enough to say that this is indeed a great honor. What I'll do over the next 1 hour is to try to convince you in a scientific story that we need to reconnect our societies with the biosphere, because now we have enough empirical evidence, which we've never had before, that we are, in fact, as the world, 7 billion people multiplied by our industrial metabolism, a geological force of change at the planetary scale. We must now become planetary stewards of our own future. And it all starts with what I would argue being the most important scientific message in modern time to humanity, namely that we have now become a geological force of change. In fact, there is so much empirical evidence to suggest that now we've entered a whole new geological epoch, the Anthropocene, anthros for us humans. For my students at Stockholm University, I normally say that we now need to navigate a 369 world. Just from September 2013, I had to change this to actually navigating a 4610 world. We are, according to the IPCC's fifth assessment, the United Nations Intergovernmental Panel on Climate Change, on average moving towards a 4-degree future this century. A place we haven't been, in fact, for the past 4 or 5 million years. We are in the 6th mass extinction of species, the first to be caused by another species. One of those 6 being when we lost the dinosaurs 65 million years back. And we are committed to not 9, but most likely 10 billion co-citizens on Earth just in 36 years. Everyone with the right to development. This is the new reality humanity faces. We've actually, up until recently, been able to operate the world according to our economic paradigm, according to our institutional paradigm, as if we were a small world on a relatively large planet. In fact, that paradigm worked quite well, I would argue, and will argue, up until roughly 1990, where we all still had space where we could shove our environmental impacts to a resilient, biophysically forgiving Earth system. But since 1990, this mode of operating comes to an end. We are today actually operating a large world on a small planet. We have, as Professor John Schellenhuber is heading the Potsdam Institute of Climate Impact Research, come to a saturation point. We're starting to see what Will Steffen, professor at Australian National University, calls that we are, as humanity, starting to hit the hardwired, biophysically limited processes at the Earth system scale. To put it simple, we're hitting the ceiling of the ecological capacity of the Earth system to support the world. And this is a completely new juncture, and it's a juncture that the science is put in place just over the past decade. In fact, the first synthesis that really puts the empirical evidence behind the Anthropocene lands on the table in 2007. So we can truly talk about a planet under pressure. A planet under unprecedented pressure of what I've called a quadruple squeeze. A squeeze from human pressure, from climate change, from ecosystems, and the recognition that the world is not behaving as we previously thought, because instead of being an Earth system that changes in a linear, incremental, and therefore predictable way, which is the basis upon which we build our economic theory and therefore also our economic applications, the world seems to behave completely different. Long periods of incremental change, as long as resilience still is robust enough to buffer impacts, can suddenly, when a trigger hits in an unresilient system, cross a threshold, and we can see abrupt changes when feedbacks change direction and the system swoops over into a different equilibrium. And I'll come back to exactly what the science shows in terms of these risks. Let's go through these pressures just very briefly to understand that this is indeed an integrated social ecological complexity of a completely new scale. So often we talk about the human pressure as being the number of people. We're 7 billion people today. We're committed to 9, potentially 10. But all evidence shows that that's not the key driving force. The key driving force is this. This is the OECD's projection of economic growth over the next 36 years. A staggering prognosis of a 300% growth in GDP in the world. A tripling of the world economy in one generation. The reason for this is shown in red and yellow, which is the extraordinary success of developing nations now going to scale with economic growth at a projections of up to 500% growth. Now this is incredibly positive. This is the majority of poor now stepping up into the development ladder, and we can you imagine, envisage a world where the rich minority becomes the majority. We're actually projecting a world with not 1.5 billion middle-income citizens in the world, represented roughly of the OECD nations, but in fact a world of 4, 5, 6 billion middle-class citizens, equivalent to an average European consumer today. That's an enormous going to scale with the social momentum, and if adopting the lifestyle that have caused the environmental problem so far, an enormous exponential increase in pressures. The second squeeze on the planet is clearly the most urgent challenge currently, anthropogenic climate change. The fact that we see, however we kind of observe change in the world, that we are following the path towards, on average, a 4-degree warming. And that's seen very clearly from the evidence on the left-hand side. You recognize the red projections of the worst case IPCC scenario, which is the one where we're just continuing to emit greenhouse gases, population growth is at a maximum, and the black dots there shows observations, in fact, that we are following this, what I would argue to be an unacceptable future. The window toward the blue line is still open, but only for another 5 to 10 years. So I'll come back to that, but we're now at an absolute urgent point in terms of the need to bend the curve away from potentially disastrous outcomes in the future. The right-hand side shows something very dramatic, that more and more climate models shows that we are at the branch point right now where it is potentially just a little more emissions that could trigger changes where the Earth system takes over warming and self-accelerates, meaning that we would just be the aperitif, meaning that our emissions of greenhouse gases, it what triggers different changes in the Earth system that can self-reinforce warming, such as the thawing of the Siberian permafrost, releasing vast amounts of methane, such as changes in color in ice, meaning that the surface on Earth becomes darker, absorbing more of the incoming heat from the sun, such as shifts in the carbon sinks in the biosphere, which could self-reinforce warming. That's also something that is part of the risk story. The risk story, I think, is best illustrated in this graph, which is just a reminder of the enormous, let's say, careful, respectful view we should have on the stability of your system. This is ice core data of the past 2,000 years, showing, you might not see it from the back, but believe me, on the y-axis is degrees Celsius variability, which varies over the past 2,000 years with only plus minus 1 degree. And that is the stability we've seen, in fact, in the past 10,000 years during the entire Holocene interglacial equilibrium we're in today. And this is if we would go to 4 degrees, meaning that a 4-degree future is not only slightly outside of the current equilibrium, it is incredibly far away from anything we've seen on Earth for the past 10,000 years. Now, it is so important to recognize that we generally tend to talk about average risk, about the average risk of moving towards 4 degrees, which already is a risk which is beyond acceptable. But I just want to share with you the importance to also recognize the risk of outcomes which are less likely, but because they are so unacceptable, we need to understand that probabilities even below 50% really matter. And this is one way of illustrating that. You may be aware that 2014 will be a very important year in terms of concentration of greenhouse gases, because we're very likely to end this calendar year reaching 450 ppm, the concentration of all greenhouse gases this year. We are already today at 400 ppm for carbon dioxide, and the rule of thumb is that you can add another 50 to be able to get the concentration of all gases. Now, this is significant because already at the third assessment of the IPCC, and building up to the climate summit in Copenhagen in 2009, there was a general agreement, even though not so strong scientific support, but a general agreement that 2 degrees Celsius is a maximum allowed limit. It was even written into the Copenhagen Accord, a very important maximum limit of warming. But it was also agreed that that, with a very high likelihood, was equal to 450 ppm, meaning that 450 ppm is a ceiling, which means that in 2014 we reach a ceiling. But let's ask the following question. What's the probability at 450 ppm, the current concentration therefore of greenhouse gases, most likely at the end of this calendar year, of reaching on the x-axis unacceptable levels of warming? And the probability at current concentration of reaching 4 degrees is 7%. But let's take something even more extreme. I'll choose 6 degrees. Now, why choose 6 degrees? Well, it's a very pedagogic number because I would argue, and you can argue with me afterwards, that there's not one citizen on Earth that would accept 6 degrees. Not even one climate denialist in this world would disagree that 6 degrees is utterly and totally unacceptable. In fact, a 6-degree world, according to anyone who still believes that we live on an Earth which is a circular planet, will agree that 6 degrees is beyond anything that can support the modern world as we know it. So the probability of this totally unacceptable level of warming at current, soon to be reached concentration is 1.6%. Now, do you know what that equals in insurance business terms and other areas of society? Well, it would be the equivalent of us accepting 1,500 aircraft crashing every day. So it proves that we are already today approaching a point of risk which we would never accept regarding a catastrophic outcome in any other sector of society. In fact, it's so serious that, as you may be aware, insurance companies like Munich Re and Swiss Re are increasingly considering and being concerned that they cannot issue premium for reinsurances at the current level of risk of catastrophic climate events because the liabilities become too high. So we're approaching a point where we need to understand that risk is an integral part of the story in the future. The third pressure is clearly that if you disturb the climate system, as we're doing, so when we emit greenhouse gases, what we're doing is that we're destabilizing the energy balance on Earth. Now, if we do that, meaning we're injecting more heat to the Earth system, you would have wished that you had a resilient, strong planet to deal with that disturbance. Unfortunately, we know from very good empirical evidence that that's not the case. The last 50 years is a remarkable journey of undermining the resilience of the biosphere, which means that we are degrading our ecosystems. Deforestation, land degradation, overfishing, acidification, eutrophication, to a point where we today know that we have never lost so many ecosystem services, the function that keeps the system resilient, as in the last 50 years. So we're at a point, for example, we're now learning that cutting down rainforest, here's a picture from Borneo, from palm oil, is not only an issue that degrades local biodiversity, or has great negative impacts on local communities, it actually leads to increased frequency of forest fires. It leads, therefore, to increased soot in the atmosphere, contributing to the Asian brown cloud, destabilizing the Southeast Asian monsoon, with potential feedbacks even in the climate system. So we're coming to a point where ecosystems regulate the stability also of the climate system, which means that we need to recognize that ecosystems are part of the squeeze in the overall planetary scale. It's actually to a point where some analysis here led by Tony Barnowski and colleagues showing that at the current pace of loss of biodiversity, we may approach a point by mid-century where we could actually have a planetary tipping point where we would lose large parts of the biogenetic diversity on Earth. But this is the risk pattern with regard to the third pressure on ecosystems. And the fourth one then being the fact that the Earth system is not responding linearly. We need to consider thresholds, and when you consider thresholds, when you simply cannot optimize because the system is not linear, what do? Well, you back off a bit from the threshold. And if you back off a bit, it actually means that our degrees of freedom are slightly lower than if we would run ourselves all the way to the brink where marginal cost equals marginal benefit. So the space for humanity shrinks slightly. So that's the reality of a world in the Anthropocene with a quadruple squeeze of affluence, climate change, ecosystem crisis, and surprise. Now, that's a dramatic message. Do we have scientific support for this evidence? And I will argue very strongly, yes. And it comes from this kind of data, which is the data of exponential rise in pressures from observations since on the x-axis, the Industrial Revolution in 1750, all the way to today. The darker curves on the left-hand side is the social momentum of this change. The population growth, even manifested, for example, in the number of McDonald's restaurants, showing, as you see, the same kind of exponential pattern. And on the right-hand side, in lighter colors, you see the hockey stick patterns of growing human pressures. And we tend only to talk about one hockey stick, which is the upper left-hand corner on carbon dioxide. But I can tell you, you can pick virtually any parameter in the Earth system that matters for our human well-being, and it looks the same. Be it biodiversity in the lower left-hand right corner, be it eutrophication, loss of forests, air pollution, deforestation, nitrogen and phosphorus overload, they all look the same and have this pattern. In fact, it's quite remarkable that if you put all these curves in the same graph, you see a pattern very clearly that up until the mid-1950s, we had a very small impact at the planetary scale. We had massive local environmental challenges, not least in the early industrialized countries like in the UK, but we did not impact the Earth system as a whole. But in 1955, 10 years after the Second World War, we're 3.5 billion people, and that's where we seem to put in the high gear of change. We move into what science today has baptized the moment of the great acceleration. And off we go on this exponential journey with regard to essentially all parameters from the atmosphere, the cryosphere, the biosphere, the stratosphere, influencing and ultimately defining our own future. The warnings came early, as we all know. In 1962, Rachel Carson writes the seminal book Silent Spring, warning humanity that we may be facing a chemical breakdown because of our industrialized societies. 10 years later, Limits to Growth, the Club of Rome, comes out with its report predicting that sometime 2020, 2030, we might actually get a drawdown of the global economy because of the human pressures on the Earth system. What happened with these warnings? Well, they were shot down. They were shot down by conventional economists. They were shot down by policymakers. They were shot down by business leaders. I would have an argument with that. But look at the graph. I would even say perhaps they could be excused, because there was no empirical evidence to stand on that they would be right. In fact, today we know that Rachel Carson and the Club of Rome were very early, foresightful voices which did not have empirical evidence to stand on. Today, we're up here. Today, we're the first generation to stand on a mountain of empirical evidence with no excuse to act. We're not in the situation in 1962 where we could say that, well, there's so much uncertainty, we don't really know if this is really correct. We stand on empirical evidence that these curves exist. And we stand on empirical evidence that they start having impacts. In fact, we're standing on empirical evidence that the Earth system is sending invoices back to the economy for the first time, which we've never ever seen before. This is truly a different situation. And I emphasize this so strongly because we environmental scientists tend to always say, oh, but now you're shouting wolf, wolf again, and you've been warning for 50 years. That's not the case. It's absolutely not the case, because the warnings that came from 50 years back are very different in character. We did not have empirical basis and the enormous mountain of knowledge we have today 50 years back. It is truly a new situation. Nobody proposed that we were in the Anthropocene in the 1960s. Today, we do it on empirical evidence. That's a big change. Is it so then that the Earth system is starting to send invoices? Because the Earth system has never done so. In fact, the Earth system has been our best friend. It's been buffering essentially all our environmental pressures up until very recently. But now, I would argue, we're starting to see the first signals of something potentially happening. This is very, very complex. It is always going to be associated with a lot of uncertainty. But when Hurricane Sandy, 2 years back, suddenly surprisingly veers right into Manhattan and puts even Wall Street 3 meters underwater, a cynical reminder that the financial system is connected to the biosphere. Science after that showed that it's very difficult to explain the sudden veering of hurricanes year after year veer right out of the Atlantic without considering the fact that we know that the Arctic vortex collapsed 2 years before. And the Arctic vortex is the system that holds cold air up in the Arctic. When this collapsed, you get high pressure cold air pushing down lower altitudes under certain climatic conditions, which could explain how this hurricane was suddenly veered right into land, totally unexpectedly. We also saw freak winter events in the part of the world where I come from, in Sweden. Now, we also have more and more evidence that methane release under the seabed in Siberia is starting to occur in a way which way exceeds what was expected. We also have more and more science indicating something very dramatic, that the Arab Spring, which of course was triggered by tremendous social momentum of a young, connected, intellectual generation rising against 30 years of dictatorial rule, would be difficult to come to scale if we don't also factor in the food riots that we had 2 years before due to 350% rise in phosphorus prices, the most important fertilizer, 120% rise in oil prices, and the fact that President Putin and Prime Minister Vlad in Australia, Putin in Russia, shut the export borders of cereals because of unprecedented forest fires in Russia and 12 years of drought in Australia. Now, if you mesh that all together in a social ecological analysis, you can no longer exclude that this is the first example in human history on Earth where social ecological interactions abruptly collide and destabilize societies at a regional scale. Now, of course, again, uncertainties are large, but you cannot exclude it. And just a few months back, Peter Glick published this paper, which shows that 4 years before the civil war in Syria, we have the worst consecutive drought years ever measured. Probably the worst drought years since agriculture was invented 8,000 years back in Mesopotamia, in this region. And we know as a fact that 2 million rural inhabitants had to leave rural areas and move into cities like Aleppo right before the civil war broke out. Again, the causality is extremely complicated. Nobody can claim that this is a driver of what's happening in Syria, but clearly this is something that is occurring simultaneously with these kind of social disruptions. This is the world of the Anthropocene. This is the world where we can no longer exclude the Earth system sending invoices. We know that the frequency of extreme events is increasing. We know that heat waves are at an unprecedented level. We know that the 2003 heat wave in Europe, which killed 40,000 people, the worst environmental disaster in Europe ever, in fact, has and cannot be excluded or disentangled from anthropogenic climate change. We know that the number of reported disasters, so-called natural disasters, are on the increase. And look at where the rise comes from. It's the green category here, which is floods. The number of floods are increasing exponentially. And this is something that can no longer be, again, disentangled from human-induced climate change. So we're in this turbulent era that Thomas Friedman of New York Times has, I think, very eloquently put to say, we all recognize we live in a hyper-connected world, socially, financially, trade-wise. Now we need to recognize we live in an interdependent world where we actually start seeing links between the biophysical changes we're occurring at the global scale and the social changes. And therefore we need to understand that the capacity of the system to stay stable is something we need to recognize. Now, we've been doing a lot of science over more than 30 years trying to understand what is it that destabilizes ecosystems. This originates all the way back to Buzz Holling's research in the 1970s, where we learn more and more that ecosystems from wetlands, forests, coral reef systems have multiple so-called stable states. We often illustrate that with this cup and bowl diagram where the ecosystem as a bowl resides in a cup. And if this cup is deep, it can take a shock like a disease or a drought or a flood, and it will roll inside the cup. It has a good capacity to buffer. It's like us humans. If you're very strong and well-trained, you can take a few punches before falling down in a boxing game, but ultimately, at the final punch, when you've lost enough resilience, the cup becomes more shallow and you risk topping over a tipping point and change state into something very differently. And we have so much evidence today to show that systems can stay stable, for example, in a savanna state, but during very long periods of land degradation, they can, over a period of a disease or a drought, top over and become permanently desertified as a shrub system. And we also learned that a rainforest system can go through the same kind of development and abruptly shift over and become a savanna. Hard coral reef systems, under overfishing, eutrophication, sedimentation from agriculture, and heating of oceans, can over a period still resist change, but then abruptly, for example, in a year of bleaching, tip over and become a permanently lost system in terms of its hard coral diverse system and shift over into becoming a soft coral system. We learn more and more that these tipping points do exist, and interestingly, we're starting to learn that they occur at larger scale. We've tended to look at them at local ecosystems, a flip between a oxygen-rich lake to a eutrophied lake, a patch of forest into a grassland. Now we're starting to see evidence that these abrupt shifts can occur at the larger biome scale. For example, at this scale. This is Svalbard. This is how we would like to see the Arctic, as a stable white system reflecting 90% of incoming heat back to space, a permanent stable ice state. But the unprecedented melting in the Arctic means that we suddenly need to explore and understand whether a system like this could in fact top over a tipping point and irreversibly move into a state which is ice-free. Now, is this even something we need to consider? Well, recent data show that we may actually have to do so. You may have seen this graph. I find that to be one of the most dramatic observations we have in recent years, because this is data over Greenland. And it is data showing days of the year on the x-axis and the percentage of incoming heat from the sun that is reflected back to space, what we call albedo. Now, in color here, you see the stable state of what we depend on, which is a permanent ice state of Greenland. So what you see is that roughly 90% goes back to space in wintertime. It goes down slightly when the coastal zone or rim of Greenland is melting naturally during summer periods, which means that you get a layer of water, which is slightly darker, which then absorbs a bit more of heat. But look at the black line. This is 2012. For 2 weeks in July 2012, for the first time in observed history, the entire Greenland ice sheet is melting. And it's not as if the whole ice sheet is melting, it's a top layer which is suddenly covered by water. And for the first time, Greenland goes from being in a logic of a cooling system with a feedback that actually reflects heat back to space. We call that a negative feedback, a feedback that actually self-cools. It actually works as a planetary scale air conditioning, to a point where actually more than 50% heat is absorbed, which we call a shift from a negative feedback to a positive feedback. Greenland suddenly becomes a foe and becomes a heating system, absorbing more heat than it reflects back to space. These 2 weeks, this momentary 2 weeks, have been calculated by Jason Boxer and colleagues at the Barrett Institute to be equal to an injection of 300 new exajoules of heat into the atmosphere. Now, 300 exajoules is a big number, but just consider the following. The annual consumption of energy in the world is 600 exajoules. The US consumes 200 exajoules per year. So momentarily, Denmark bypasses China and the US as the world's largest climate-forcing nation on Earth. When Greenland shifts her feedback, that is why the Earth system is such a powerful engine under the hood. That's why the little silly statement of humanity potentially being the aperitif. Because when the main course starts and the Earth system takes over, that's when the big, powerful shifts may occur, and albedo being one of the largest ones. Well, you see, we always thought that this was something we really need to be concerned about in the Arctic, but more and more science shows that Antarctica is showing proof of being less resilient than we previously thought. And a few months back, in 2 independent studies, another scientific nightmare suddenly came to the fore from observations. This is work showing for the first time that a few of the glaciers in the West Antarctic ice sheet may have gone across a tipping point and are irreversibly sliding into the ocean. Because the ice glaciers in West Antarctica, which stand on rock, are standing there firmly thanks to ice plugs that keep them firm on the rock. But these have now melted due to warmer ocean currents, which means that they are now irreversibly sliding into the ocean. And when one of these get released, more will follow. The conclusion in these 2 studies is that we are therefore in for another 1 meter sea level rise this century. Now, as you may be aware, the UN IPCC assessment, which is very conservative, assesses on average that we're facing a 1 meter sea level rise this century. So this adds another meter. This means 1 + 1, 2 this century. Now, I was sitting in the car a few months back and trying to, because we always talk about 2100 being so far away. And there was this interview with a young teenager, and she really punched me in the stomach because she said, you know, I'm really worried about climate change. And I'm worried about climate change because I want to have kids. And I realized that when I have kids, my child who will be adult will actually be alive 2100. So I checked a bit on the statistics in Sweden, and an average boy or girl has life expectancy in Sweden 86 years. And it's 2014. So on average, every child born in 2014 in my country will be alive in 2100. This is not far away. 2100 is not far away. 2 meters in 2100 is like tomorrow. So that is an incredibly important reminder that this is really a situation where we need to move very fast on some of these agenda items. We now learn that big systems also in the ocean may shift very dramatically from this desired state, which actually supports 250 million people on coastal regions in the world through fisheries, tourism, and all the ecosystem services that thriving, diverse coral reef systems provide. Potentially, we see large attractive systems tipping over into this kind of undesired state. In the IPCC, there was this very dramatic first-time synthesis around what's the implications of a 2-degree warming on freshwater supply in the world. First victim often of climate change. And what you see here already, 2 degrees warming, and this is, by the way, a remarkable study because it's the first time that the ensemble of climate models are gathered with the ensemble of global hydrological models. And what you see here is in red, regions that are predicted at 2 degrees warming to have 25% or less rainfall at that state. Now, if you get 25 or 30% less rainfall, you're likely actually to move out, for example, of farming, rather than just having lower yield levels. And look at the map. Look carefully where the red zones are. Just look at North Africa and Southern Europe. These are regions very close to home, so to say, that may be very, very harshly affected. You see the US there with very high degree of impact in the central and western parts, and you may be aware that the central parts of the US are experiencing the worst drought on record right as we speak, and the San Joaquin Valley in California is having an unprecedented drought right now as we speak. So these are extreme events occurring right now. And the synthesis on this is, I can tell you, very profound today. This is a famous map brought forward by Tim Lenton and John Schellnhuber on the different systems that may actually go through abrupt shifts under climate-induced changes. So you have the West Antarctic ice sheet, you have Greenland, but you also have the risk of, for example, a dieback of the Amazon rainforest. We recently published a book in Cambridge University Press on the fact that we see similar evidence with regards to water-induced tipping points. So this is, and I do a kind of a little halt here just on the diagnostics. So what the summary is so far is therefore that we now must recognize that we have two giants colliding. The first giant is the fact that now is when we go to the social momentum of big change in the world, where the rich minority will become the majority in the future. It is occurring now, which is very positive, but an enormous challenge. And the second giant colliding is that we, for the first time now, start seeing evidence that the Earth system is starting to send invoices back, and we can see feedbacks changing where you might see reinforcing shifts in the wrong direction. And that's the reality we're in. Now, then to address that, what can we do? What does science do to be able to step up to this challenging Anthropocene? Well, that is where the planetary boundary framework starts evolving. And the first question we then asked ourselves was the following. Can we define the desired state of the planet? What state do we want the planet to be in to support the modern world as we know it? And then we have to look at the stability of our recent history. And the question is, are we leaving Eden's garden? And we have a lot of evidence that we actually can learn from in the past. You've seen these paleoclimatic data showing ice cores back 1 million years. And this is the classic Vostok ice sheet. It's remarkably, it's almost like a piece of art in my mind, showing our 200,000 years cycles between glacial and interglacial periods, all the way up to the last interglacial, which is called the Eemian, where we had several thousand years of similar warm conditions as today, how we dig ourselves down in the last ice age, come out and enter the Holocene, which is where we've been for the past 10,000 years. We know that the last time we had 2 degrees warmer than today was in the Eemian, 120,000 years back. At that time, we know quite with high degree of certainty that sea levels were 4 to 6 meters higher than today. So we can learn so much from the past in terms of how the Earth system was and how it was to live on Earth at previous phases in our history on Earth. This just leaves us humbled in terms of the stability of the Earth system and how the Earth system self-regulates between glacial and interglacial. But the much more important and exciting period is to just look at the most recent 100,000 years. So I've taken out from the previous slide here the last 100,000 years, the last little piece from 0.1 to 0 there, and it looks like this. Now, this is 100,000 years, which is a very important period to slice out because we've been modern humans on Earth for 200,000 years. So we've had the same physical and intellectual ability to develop civilizations as we know it. And what you see on the x-axis here is temperature variability, which is a good proxy of how it was to live on Earth. Now, what you see here is that for most of this period, it was a very jumpy ride for humanity indeed. In fact, it could vary in a decade with plus minus 5 to 10 degrees Celsius. It was so jumpy, in fact, that at a cold point, the one at roughly 75,000 years, science indicates that we were probably down at a remarkably low number, at so few people on Earth as 15,000 fertile adults. We were virtually extinct. We were hiding in the Ethiopian highlands, the only place on Earth where we could still find fresh water and biomass, most of the water tied up as ice in the poles, sea level 70 meters lower than today, an example of how incredibly tough it was to live on Earth. We were actually just a few million people on average during this entire period. We were hunters and gatherers. We had, to put it very simple, a rough time. Until we exit the last ice age and enter what is shown in the right circle here, what I would argue is our Eden's Garden. This is the Holocene. This is the last 10,000 years of interglacial, where temperatures on average vary with only plus minus 1 degree Celsius. In fact, it's so stable that we barely enter the Holocene and we do the most important, we come up with the most important invention ever in humanity, which is we invent agriculture. We domesticate animals and plants right at the beginning of the Holocene. And it's so exciting because we do this independently at least 4 different places on Earth. And because we didn't have smartphones and Twitter and email and stuff at that point, we can prove that this had something to do with the stability of the living conditions on Earth. In fact, I would argue that we have enough evidence today to say that the predictability of rainy seasons, the fact that year after year we knew that we had 90 to 100 days at least 15 degrees Celsius temperature with at least 25 stable rainfall events, probably was the reason why we went from hunting and gathering to becoming sedentary farmers. And that stability, the predictability and stability of the Holocene equilibrium, enabled us then to start the differentiation and specialization, which enabled us to go from the Mesopotamian irrigation societies to the Maya, Inca, Chinese, Greek, Roman, all the way up to the great acceleration point when we're 3.5 billion people. We're 7 today, committed to 9-10 billion people. So the scientific message is as dramatic as it's simple. The Holocene equilibrium is the only state of the planet that we know that can support the modern world as we know it. We can live outside of the Holocene. We have done so in the past. But if we take an ethical responsibility for 9 to 10 billion people, all with a right to development, the Holocene seems to be the only state that can support us. This is quite dramatic, of course, but it's also quite remarkably positive because it gives us a tool to navigate the future. Why? Because we know the Holocene very well. We know the carbon cycle, we know the nitrogen cycle, the phosphorus cycle. In fact, we know that even though the genetic diversity on Earth has been around often for hundreds of millions of years, we know that the rainforest configuration, the savanna system, the grasslands, the meadows that you love so much in the UK, and the wonderfully, beautifully layered archipelago that I love so much in Sweden, all settles in during the Holocene. Actually, everything we value in terms of natural capital settles in during the Holocene and becomes, this wonderfully accessible and stable and predictable Walmart supermarket available for us to exploit for our well-being. And this is what the Holocene really offers us, this stable access to natural capital from the global hydrological cycle to the phosphorus-nitrogen cycle, the land base, the oceans, the atmosphere, the temperatures, which is the signum of the Holocene. Now, because we know the Holocene so well, we can therefore measure the Holocene. we can not only measure it, we can even start exploring what are the environmental processes then that regulates the resilience and the ability for the Earth system to stay in the Holocene, question one. And question two is, can we for each of those environmental processes look and explore control variables that regulate them, and even based on the analysis and knowledge we have, define a variable, a boundary beyond which we risk feedback to changing direction and crossing a tipping point that will push ourselves outside the Holocene. And that is, in a nutshell, the planetary boundary framework. Identifying the environmental process that regulates the ability to remain in the Holocene, and for each one of those, define quantitatively a science-based boundary beyond which we risk nonlinear changes that could take us away from the Holocene. And if we could define quantitatively these boundaries, what does it give us? Well, it gives us a safe operating space. It gives us an area within which we can have world development. And that is what led to the whole concept of planetary boundaries. Now, there's of course an enormous scientific challenge here, which is that nobody knows exactly when you cross a tipping point where things go wrong, often until we've seen it and we can kind of measure it after it's occurred. So the challenge for us has been to map out the science and recognize the fact that for each process that regulates the Holocene, there will be inevitably an uncertainty zone, a standard deviation of uncertainty in science. And we chose, as a normative decision, to place the boundary at the lower end of scientific uncertainty as a precautionary principle. You could, of course, place it elsewhere, but it's important to recognize that the planetary boundary framework, the boundary position of the safe operating space, is not the point of the threshold. So you go beyond it, you go into a catastrophe. It's the point beyond which you enter a zone of danger. And just to give you one example, among the 9 boundary processes that we identified, let me just mention those very briefly. I think they come here as a list. We have, not surprisingly, the 3 big processes which we know from paleo research that have evidence of being able to cause planetary scale tipping points. The climate system, the stratospheric ozone system that protects us against dangerous radiation of UV. And finally, ocean acidification, where we know in the paleo record of Earth that we can see massive dead zones caused by large-scale acidification of the ocean. So these have very, very strong evidence of planetary tipping points if we push them too far. More surprisingly, perhaps, the group of scientists, over 30 global environmental change scientists that were involved in this analysis, identified 4 systems that do not have evidence of planetary scale tipping points, but systems that, or processes, that regulate the stability of the Earth system. And these include biodiversity loss, the rate of loss of biodiversity, land use change, freshwater use, and the degree of interference with the 2 other large cycles apart from carbon, which is linked to climate, namely nitrogen and phosphorus. And these processes, they operate under the hood of the Earth system to regulate and buffer changes in the Earth system. For example, the stocks and sinks of methane and carbon, the ability of the ocean to store heat, the ability of forest to store carbon. These are systems that operate in the living biosphere to try and regulate the pressures that may occur naturally or from humans in terms of impacts in the Earth system. And then we had 2 processes which are a little bit different, which we in fact couldn't even quantify boundaries for, which are much more anthropogenic in their origin. The first one is chemical pollution. The risk that we, either through loading of nuclear agents in the biosphere or by inventing so many chemical compounds which aggregate into potentially even affecting the genetic composition of species, could actually cause a tipping point in terms of living conditions for us humans. And finally, atmospheric aerosol loading, which is the particulates, the pollution in the air, which we're already causing, which we know as a fact can have large impacts at the regional scale. For example, as I mentioned earlier, the Asian brown cloud impacting on the Asian monsoon. So these are the 9 planetary boundaries which were suggested in 2009 and first published as a proposal to challenge science originally in terms of a new framework for development in the world of the Anthropocene. Meaning that now we need to think truly about being stewards of the processes that regulate the stability of the Earth system in the Holocene, and that we therefore need to navigate a world within a safe operating space. I can tell you that this triggered an enormous amount of scientific debate. It has actually, since its publication, resulted in no less than 62 scientific publications and almost 1,000 citations in the literature, which is quite significant, but also major discussions in policy and business, and actually taken itself to a point where it's now recognized as being potentially a framework to guide the translation of the so-called Millennium Development Goals from the United Nations into the new framework of Sustainable Development Goals, which replaced the MDGs from 1st of January 2016. That is not because this framework came from the sky and popped down on the table of policymakers. It's of course because it's a natural incremental step of knowledge advancement from the enormous advancement in Earth system science over the past 30 years. That the recognition that we're in the Anthropocene in terms of pressure, the recognition that we have nonlinear changes in terms of tipping points, when you combine this together, leads quite naturally into this kind of framework of thinking in terms of our own future within the safe operating space on Earth. Now, we're currently working on an update, and I just want to share with you that update, which builds on the critique we've received from many, many peers around the world, actually has led to one conclusion, that the 9 boundary processes stand robust. We were actually challenging ourselves to say perhaps we've missed something, or perhaps we've taken in one too many, but in fact the 9 stand strong, and we've improved the quantifications, particularly for biodiversity. We have a lot of evidence to suggest that we are actually in a danger zone on phosphorus, which we didn't think in the first analysis. And for the rest, we have some degrees of freedom, as you see, still with regards to land and water, with regards to aerosol loading, and with regards to stratospheric ozone depletion, where we were in a danger zone until we signed the Montreal Protocol, which took us back into a safe space with regards to the protective stratospheric ozone layer, proving that we can become planetary stewards. We've done it once before for ozone. Now, I will just spend the last 10 minutes to say, what does this really imply for us in the future? Well, I can tell you, and I really hope I get this across, it fundamentally changes our development paradigm. It means, for example, for the first time, that we need to consider how we share in a fair way absolute budgets of the remaining space on Earth. We've never had to think of that way before. We've actually focused a lot of effort, even successfully, to kind of become more efficient by being relatively more efficient on, for example, emission reduction or energy efficiency in housing or relatively less consumption. But for the first time, it actually means that we need to operate with an absolute budget of land use, a phosphorus budget, a nitrogen budget, a global water budget, a global carbon budget. And that, of course, means that if it's absolute, we need to divide that absolute number by the number of people, giving us an equal access and right to that share. That sounds like utopia, but as you may be aware, it's already occurring on climate. In fact, even the IPCC has this work, exactly this graph, published in this work, showing that if we want to stay under 2 degrees warming, which is a kind of a boundary, that translates to, if we still want to have a 2/3 of a chance to stay safe, to a carbon budget of roughly 1,000 billion tons of carbon dioxide remaining to be emitted. That 1,000 is an absolute number. It's an actual absolute budget if we are going to operate within a safe climate boundary. We've never considered that for anything else in the environmental space, but now, for example, this analysis shows that if we want to feed the world, we cannot do it by expanding agricultural land. We need to do it by actually sustainably managing the current land we have, because we cannot sacrifice the remaining forests and grasslands if we are serious about maintaining an Holocene state. It actually means that we need to understand that we have to become planetary stewards of the entire biosphere. Now, the most pedagogical way of showing and proving that is this graph, which I find each time I see it to be so mind-boggling. We have, since the Industrial Revolution, emitted a staggering 545 gigatons of carbon. This is carbon, billion tons of carbon, from emissions from industrial development and land use change. But is it that 545 which has led to roughly 1 degree Celsius warming so far? Well, as we know, no. Because the atmosphere Because oceans and land have absorbed 55% of those emissions. It's only half of our emissions that remain in the atmosphere. And this is significant because carbon dioxide is a long-lived greenhouse gas, staying in the atmosphere for at least 1,000 years. Now, the fact that 55% of our emissions of greenhouse gases from burning of oil, coal, and natural gas is taken up by oceans and land is, in my mind, no doubt the world's largest subsidy to the world economy. Now, the most remarkable, though, is not that. The most remarkable is the following: that 50 years back, that fantastic service to humanity was estimated to be 2 billion tons of carbon per year. Now, the estimate is that it's up to 4.5. So over just 50 years, the Earth system has doubled the amount of carbon taken up in nature. So what is going on? Well, what is going on is very simple. The Earth system is applying its biogeochemical processes to remain in a stable, resilient Holocene state. It still has resilience to be our best friend. It is actually dampening the impacts of our emissions of greenhouse gases. But it leads to ocean acidification, and it leads to increased biomass in some parts of the world, but potentially also saturation in the future. So this is a proof that we need this integrated approach. We actually increasingly have proof that big biomes in the world do matter for regulating this stability. That for any nation in the world, actually sometimes argue that a finance minister, even a small country like Sweden, must be equally concerned as President Dilma in Brazil about the rainforest, as Denmark is about Greenland, because these are big biomes that regulate the resilience of the entire world economy. We can no longer operate only as nation states. These are obsolete units to navigate the Anthropocene, because we all depend today on the capacity of the big biomes to operate. Then, of course, changes everything with regards to action, because if you want to transition into a safe operating space, we need to recognize that it's not a small transition that needs to occur, it's in fact big transformations. And I will argue in the final part here that there are 3 transformations that are more urgent than anything else. One is a transition to a decarbonized world economy, meaning moving away from fossil fuels by mid-century or by 2060. Secondly, a transition to a sustainable food system in the world. And thirdly, start a transition to a circular economy. Now on food, this is really exciting and important and an enormous opportunity because, well, you're all familiar, of course, with the debate between conventional agriculture and ecological agriculture. I will argue that no agricultural system in the world lives up to the criteria of planetary boundaries. Because in fact, now we need to recognize that food should be produced in a way that goes from being the world's single largest sector emitting greenhouse gases to becoming a carbon sink. Not even organic agriculture does that. It has to be a system that is no longer the world's largest consumer of fresh water. A system that does not expand land and therefore being the world's largest single cause of loss of biodiversity. We can now quantitatively define the criteria for sustainable agriculture. And if we get it right on agriculture, we can actually tick off a large part of the challenge of navigating a safe operating space. Can it be done? Well, recently a study led by John Foley at the University of Minnesota showed that yes, we can actually feed humanity, even 9 billion people, on current cropland. It will require massive efforts, even changing diets, reducing waste, but we can actually increase productivity on current cropland in sustainable ways to feed humanity. And if it can be done within a full safe operating space is still to be answered, in my mind, a great scientific question. But it's one of these enormous untapped potentials. Can you imagine a world fed through sustainable agriculture, which thereby allows us to have a win-win because we could allow and contribute to a stabilization of a Holocene state? On energy, the global energy assessment show that yes, we can bend the emission curves and stay within the 2-degree boundary, but it will require an enormous effort in terms of wedges towards a broad portfolio of different renewable energy systems. It probably will require that nuclear power remains in those parts of the world where it exists today, but it can be done. And I think there's a lot to say about these hockey sticks, which is the extraordinary exponential rise of wind and solar since 2002. Yes, of course, it's only 2% of the world energy mix today, but if you wake up a Saturday morning in Germany, the world's 4th largest economy, you're actually likely to get at least 30% of your electricity from wind and solar. India produces 3% of its energy today from wind and solar. So these are actually competitive technologies that are now going to scale at a large level. The European Union recently finished its European Resource Efficiency Platform, which shows that, in fact, Europe, not on environmental grounds, but for competitiveness reasons, should move very fast towards resource efficiency in all its business models, but ultimately towards a circular economic development, meaning that we should recycle all materials, all ecosystem functions in our business models to be competitive in a world not only of 10 billion people, but where the majority is actually demanding and competing for resources. So this is quite an exciting future where more and more evidence shows that this can be done. And we're starting to see many businesses thinking in these terms. For example, when electric hybrid cars are put to the market, where batteries are withheld and owned by the car companies as a service to those who buy hybrid cars through the life of the entire vehicle. So those are just 3 urgent transitions. Now, what does it mean for governance then? Well, clearly it means we need to rethink the economy. We always thought the economy as being land, labor, and capital as separate parts. We evolved this quite nicely towards thinking about natural capital, which was Gretchen Daly's last year's Humanitas Professorship focus, social capital and human-made capital. Now we need to put these together into a new paradigm, which is that the economy should operate and serve society within a safe operating space of a biophysically stable Earth system. It is truly a change in paradigm. It actually changes sustainable development quite profoundly. You've always, and I think we all are so in awe of the Brundtland definition of sustainable development as the 3 pillars of development, of social, ecological, and economic development. Now, I think we have evidence to say that this didn't really work. It became a Mickey Mouse economy instead, where the economy grows at the expense of social and natural capital. And that we need to transition into what recently was put forward to the United Nations and out in the scientific literature as meeting the needs of humanity, defined by all nations in the world today, after all. That now the Sustainable Development Goals of the UN sets out to eradicate poverty, to eradicate hunger, to secure education and health for all, and also secure economic growth, but that this needs to occur within science-based definitions of global sustainability criteria. I'm at least quite excited about this development because the draft of the Open Working Group of the UN, as you may be aware, of the 17 Sustainable Development Goals that are suggested, among those there are 4 goals which are planetary boundaries. There's a climate goal, there's an ocean goal, there's an ecosystem goal, and there's a freshwater goal. Now, they're not yet quantified properly, so we have some work to do. The General Assembly in the UN is actually deciding upon this in September next year. But we're starting to see the contours of a framework that starts to think in this way. In the Anthropocene, with the risk of catastrophic tipping points, where invoices makes the risk too high, let's define social goals which are aspirational, but lock them within a safe operating space. I think there's reason for encouragement also by the fact that 400,000 people walked through Manhattan during the Ban Ki-moon Climate Summit just a few weeks back. 400,000 people is quite enormous for a climate demonstration. The last time it happened was 100,000 people walking through the streets of Copenhagen in 2009. I was incredibly impressed by this. Ban Ki-moon was at the front, but also you had the entrepreneurs there demonstrating because of the innovations and opportunities of a transition to a low-carbon future. You had the middle-class parents with their kids walking there. These were not the environmental extremists demonstrating. This was a social movement of the opportunities of a decarbonized future. Business leaders are actually showing the same message. This is the World Economic Forum's famous global risk report showing what business leaders in the world find to be the biggest risks in the world. And of course you have global governance failures, you have corruption, financial crisis. But the big red rooms there, look at what those say. Food security, water security, climate change, air pollution, biodiversity loss, flooding. This is the recognition among business leaders that we cannot have successful business in destabilized, dysfunctional societies because of Earth system changes. We start seeing major evidence that the awareness finally among citizenship is changing. We know quite well that in Sweden, roughly 76% that's quite an exact number by the way, roughly 75% of the population recognizes that humans are the main cause of climate change. When I describe that number, I often get the reaction, well, but you Swedes, you're so environmentally aware, and you're kind of way ahead of us all. I should say that in the UK the number is roughly the same. But through a foundation in Sweden, they therefore recently did a Gallup in different countries of the world, including China, India, and Brazil. This was an internet-based survey, so it didn't capture people in the rural regions, but can you imagine what the numbers are? I was astonished to see these numbers. That in fact, in countries like India, Brazil, and China, the awareness among citizens in general that we are in a state where things need to really change is actually seems to be deeply rooted. In the US, the number is as high as 66%. So we're kind of cheated to believe that the US is kind of way behind in terms of recognizing the challenge we're facing. I would argue that media has an enormous responsibility for the mismatch between the way things are portrayed and the way citizens actually are well aware and much wiser than the political leadership believes we are. And this is coming across very well in different documents. You probably saw when even The Economist welcomed humanities in the Anthropocene. I love The Economist, the wonderful British weekly with these wonderful, understatements. And it had a quote in this issue which I just love because it really reflects the sentiment in my mind among scientists. It said as follows, that when reality is changing faster than theories suggest it should, a certain amount of nervousness is a reasonable response. And to me, I think that really reflects the state of mind among scientists. Scientists are reacting on their own evidence. Future Earth is the largest investment ever of trying to now integrate Earth system science with global sustainability research. It's an enormous step change in science. We're actually running much more outward courses. I really want to signal that we're now starting even a massive open online course on exactly this knowledge to be shared across the world. We're starting to see actually a change from a paradigm, which closes this lecture, where we have for so long assumed that we live on a planet where we can grow without limits, which is the paradigm we're stuck in. We scientists, I think, should be self-critical to say that limits to growth was not a good story to tell the world, but instead now we have a new story of growth within limits, a story that actually allows us to secure a prosperous future for humanity on a stable Earth system, which is not a doom and gloom future. It's actually to navigate responsibly world prosperity within a stable Earth system. Thank you very much.